Good evening, everybody. Welcome to our Christmas lecture 2020. It's a little bit different this year. We've had a bit of a different year. Normally, I would be standing up on a stage welcoming you to Imperial, but here we are in our homes. But the science will be the same, if not even more exciting. I'm just going to let a few more people come into the room. Welcome. Take a virtual seat. Hope you've all got your Christmas sweaters on. Only I've got it on, and we shall get going in a second. But yeah, welcome everybody. Christmas lecture. So normally we would be on a stage in the Great Hall of Imperial in the beautiful heart of South Kensington. But this year we are conducting science from our homes, which is even more interesting and very exciting. But nevertheless, we're all learning lots at the moment. I don't know about you, but my brain is imploding with how much we're learning, even from home. So wherever you are, and it will be amazing to hear where you are all from. We hope you enjoy this evening. We've got a really good lecture lined up. And because we're doing this as a webinar, you'll be able to ask questions. So you should see a little question box. And whilst our guest speaker is giving his talk, feel free to pop a question in there. What we'd love to know is your name and where you are from in the country or world, or even out of this world, who knows? And then what question you would like to ask our guest speaker. And then after the talk, my able assistant here, young Sebastian, will be able to give the questions, and we'll get through as many as we can. There's a lot of you out there, so please don't worry if we don't get around to answering your question at the time, but we hope you enjoy what we've got set out for you tonight. Okay, I make it just after 5:30. Without further ado, my amazing co-host here, Seb, is going to introduce our guest speaker, and then we are going to go on a voyage into space.
Welcome to the Christmas Lecture 2020. This year we are going into space with Sanjeev from our Earth Science Department. It will literally be out of this world.
Enjoy, everybody. See you on the other side.
Hi, everyone. Okay, thanks for joining. My name is Sanjeev Gupta, and I am an earth scientist. Well, I was an earth scientist, now I'm an earth and planetary scientist in the Department of Earth Science at Imperial College, and I'm a geologist, and a geologist is somebody who is passionate, weirdly, about rocks and things. And most of my career I've spent looking at rocks on Earth, and about 10, 12 years ago, my career took a bizarre turn, and I ended up working on Mars by a curious chain of events that were totally unpredictable. And I spent most of my life working on Mars, and I'm currently involved in 3 different Mars missions. One's active on Mars today that I'm going to talk about mainly. One's going to be landing in February, and this is what you can see in this first picture is Perseverance rover launching into space from Cape Canaveral in July of this year. And in February 2021, February the 18th, we're going to have that scary landing on the surface of Mars to begin the journey of Perseverance. So 2 rovers operating on Mars. And then thirdly, there's another rover. It was supposed to go this year. It was the European rover, the ExoMars Rosalind Franklin rover that's actually been built in Britain. In Stevenage, and unfortunately it was delayed, and it's now going to be launching in 2022. We're all sad that it's been delayed, but actually I'm not sure my life could cope with operating 3 Mars rovers simultaneously. I think I would go slightly crazy. Okay, so let's get this journey going. So this is not Mars. We don't have oceans and seas on Mars at the present day, but this is probably the most famous rock outcrop in the world, and it's in Scotland, just east of Edinburgh. This is the rock outcrop that geologists just pay homage to, because here what you can see are these red rocks with different inclinations. And here it was worked out for the first time by a scientist called James Hutton in the 18th century that Earth had a deep time history. So these rocks, these sedimentary rocks, recorded a long evolution of the Earth that went on for many, many eons. And at that time, you couldn't say how long, but we know that we have rocks going back to almost 4 billion years on Earth. And we now know a lot about the history of Earth, its past history, what we call deep time, by reconstructing the sedimentary rock record. And that's what I'm an expert in. I look at sedimentary rocks. And we're now beginning that journey afresh on the other rocky bodies in the solar system, and in particular on Mars, which is probably the most Earth-like planet. So here we can see that Mars is much smaller than Earth. It's about a third the size of Earth, has much lower gravity. But when we look at features on the surface of Mars with rovers, they look strangely familiar. So as you will see in the pictures that I'm going to show you, if any of you have been lucky enough to go to desert regions, it looks really very similar. And so we're now building up an extraordinary picture of Mars and its early evolution from the rovers that trundle around the surface. And I'm mainly going to talk about the Curiosity rover. So at the present day, there is no liquid water on the surface of Mars. It's not possible because the Martian atmosphere today is very thin, and so surface pressure is very low. So if you put a bucket of water on Mars, it would immediately evaporate. Mars today is a cold, dry desert. It's really inhospitable. I don't think I'd really want to live on Mars. You know, people talk about living on Mars, having colonies on Mars. It would be pretty rough, actually, and there's no greenery or anything like that at all. So I think it's a great place to go exploring, but I'm not sure I'd have long-lived colonies living there. Well, it depends on what we do on Earth. You know, we need to protect Earth. So, but actually what's really interesting is that almost 100 years ago, people actually thought there was an advanced civilization living on Mars. And you can see this is actually one of my favorite newspaper headlines of all time from the New York Times, that great newspaper from 1911, where they outlined this amazing story from an astronomer, how he speculated that the Martians had built 2 immense canals in a period of 2 years because he witnessed, using a telescope, these strange lines that were called canals, canali, on the surface of Mars. And basically, people around that time, around early 1900s to about the 1920s, the general public, because of this astronomer, Percival Lowell, genuinely believed that there was an advanced civilization on Mars. And they were actually building these canals to transport water from the poles to the equator, where the Martian civilization was dying due to a lack of water. So who knows what those Martians look like? But I can tell you, we're not looking for advanced aliens like this. We're looking for tiny microbes. We don't believe that there's an advanced civilization living on Mars. And in fact, actual fact, when the first missions went to Mars, apologies, my screen has gone mad. When the first missions, orbital missions went to Mars, flybys and orbital missions went to Mars, they saw a cold, dry desert and volcanoes and crater plains. And then finally, Mariner 9 witnessed these amazing channels on the surface of Mars, these valley networks. And this was the first evidence. So people had kind of given up. But what was clear was that these canals, these valleys were dry. They had been formed by water billions of years ago, but there was no water present on the surface of Mars. So the idea of present day life was given up. And nowadays, most missions seek evidence for past life, and in particular looking at rocks. So Mars has abundant rocks from about 3.5 billion years ago. That's a very big number. That's a very long time ago. But that's the sort of time that life started to arise on Earth. And so we think that maybe, you know, life arose on both planets simultaneously, maybe. We don't know if there was life on Mars. We have yet to find it. Maybe life on Mars was seeded from Earth. Maybe life on Earth was seeded from Mars. We don't know. Maybe it came from elsewhere in the solar system. And this is what this amazing discovery would hold for us as scientists, as a civilization, as human beings. Could we discover if life actually arose elsewhere? What we do know was that Mars, early in its history, is thought to have been warm and wet. That's still controversial, but most scientists, most geologists think that Mars was warm and wet and had conditions potentially conducive for life. What rover missions are doing is trying to identify the right rocks the right habitable conditions to search for life. So what makes a habitable environment? We need certain elements, biogenic elements. We need carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur in the rocks. We need energy, sunlight, such as photosynthesis, which drives much life on Earth, or chemical energy from food or thermal energy. And we need water. And most of exploration on Mars has been dealing with searching for evidence for water, and we're pretty clear that water existed on Mars in its ancient past. You know, NASA's always rediscovering water on Mars. But what the rovers have been doing is looking for evidence for the building blocks of making a habitable environment and energy, and that's what Curiosity has been searching for and discovered. So Curiosity went to this crater called Gale crater, which is a 150-kilometer diameter crater. And in the center of it, it's got this fantastic mountain, a huge mountain, 5 kilometers high, which is made out of stratified layers. It's made out of sedimentary rocks, and sedimentary rocks are formed when erosional processes move sediment on the surface of a planet and deposit it and leave a layer. And so what they're recording is they're recording the surface environment through time. And so the idea was that you could land at the bottom of that mountain and the rover could progressively climb up a short distance, not to the top, and record the evolution of those layers and see how the environment changed. And the environment records climate. So for example, if you have lakes, you have wet environments, humid environments, but if you have deserts, that's generally formed in dry environments. And that's what we're looking for, is signatures of those environments. So that shows our approximate landing site. And we had this amazing landing system. Let me see if we can get this to work. And so this is what's called the 7 minutes of terror. So there's the spacecraft coming into Mars atmosphere. There's the main cell and the heat shield. You can see the immense heat forces on this. During this time, human operations cannot have any impact because it takes too long for a message to come back, to go to Mars and come back to Earth. So this is all being done automatically. And here it is going through the upper atmosphere. And now we set the parachutes going to slow it. So Mars has a thin atmosphere, so you still need parachutes to slow the spacecraft down. And this is the biggest parachute ever built. And now the heat shield comes off. And now we have the parachute, and soon the powered descent will take place. So we will lose the back shell. We'll lose the back shell, and that's the powered descent stage. So it's using retro rockets to position the rover towards the surface. And then we'll have an amazing maneuver where, and you can see the rover is underlying the descent vehicle coming down onto the surface. Obviously, this is all a simulation, I should say, the cartoons. And now the rover is lowered onto the surface on nylon tethers. And they have to cut the tethers. They have to put the rover on the surface and cut the tethers and send the descent vehicle sideways so it doesn't crash on top of the rover. And there we go. And so in this amazing maneuver, the sky crane maneuver, the rover Curiosity was delivered to the surface of Mars. And this was the scenes in the room. And I was in this room. I think many of the scientists didn't believe it would work. And it was just amazing, the feeling of elation. So you can see scientists are human beings. We all have emotions. Some of these people had spent 10 years developing the instruments on that rover. And they just went wild in ecstasy. It was an extraordinary moment. And then we had work to get on with. So this is Mount Sharp. That's the mountain that we landed at the base of. And we had to immediately start driving to get to the base of this mountain to begin our science. And we actually had a very, very long drive to achieve that. So here's a cartoon of the rover. And it's essentially, Curiosity is basically a laboratory geologist, a geoscientist. So here it is wearing a lab coat. We've got the eyes of the rover at the top, and where you can see the goggles. Above that, we've got a laser which measures the chemistry. And then within the belly of the beast, we've got two amazing instruments that do amazing chemistry. They work out what minerals are present in the Martian rocks, and then they take samples of rock and they heat them up to very, very high temperatures and look at the gases that are given off, and they're looking for organic compounds. The rover has 17 cameras, and it spends quite a lot of time taking pictures of itself. It's a very narcissistic rover. And here's what its most recent selfie. And it's Curiosity is very proud here because she has drilled 3 holes into the rock over there and analyzed the samples and got some really, really interesting results. So huge array of instruments in that rover here. And this is in the early days, we were all in Pasadena in California, and this is one of the rooms where we used to sit and do rover operations. And this is mainly rover engineers working with some of the scientists in planning the day's operations, basically. So the Curiosity doesn't decide what to do by itself, and we don't work in real time because of the time delay between Mars and Earth. And so we plan a whole day's of activities, stuff that Curiosity has to do. We send the commands to the rover, and most of these people are computer engineers. You know, there's about 400 scientists on the mission, but then there's another additional 250, mainly engineers, computer engineers, who write code. Apologies, that keeps happening. And send the sequences to the rover. And then the next day, the rover carries those out. So we landed in this location over here in Yellowknife Bay. We did some analysis at Yellowknife Bay, and then we drove for a couple of years, and now we're actually somewhere in here. And it's taken us, so we landed in 2012, we're in 2020. It's taken us a very long time to drive just over 20 kilometers. Rover science is slow. If it was a human, we could do this very, very fast. Well, not as fast as on Earth, obviously, because you'd be wearing a spacesuit, but with a rover, it's not so easy, and it takes a lot of time, partly because of the time delay between Earth and Mars. And we've done some amazing science on the way. So this is one of my favorite images at a place called Kimberley. And we discovered that the rocks in the foreground over here, when we analyzed them in detail, were actually the deposits of ancient deltas. And deltas are where rivers enter a standing body of water, a sea or a lake. And this gave us hints that maybe there'd been a standing body of water in Gale Crater. This was what we were after. Ancient lakes are perfect environments for life to form in, live in, and evolve in. And what scientists are interested in is finding long-lived lakes. So, but that's not, you can't do that from orbit. It's very difficult to do that from orbit. So the signs that these sediments were perhaps ancient deltas led us to consider that maybe there were lakes further towards Mount Sharp. And then when we drove further, we got to these light-toned rocks that you can see in the foreground here, these rocks over here. And that's the thing, we're about 100 meters from this rock outcrop, and yet even at that distance, we have no idea what those rocks are. And the real thing is that what we have to do as a geologist to look at the rocks is we actually have to get up close and personal. We have to use our hand lens and get down onto the rocks and look at them in detail. And Curiosity has a camera called Marley, which is basically like a hand lens. It's like a really, really, really powerful magnifying glass. And it can look at the rocks, and it can look at the grains in the rocks and see if they're grains or not, and it can see layering, etc. And that's the next clue we had. So when we got even closer to within, the next slide, this is about 1 meter from the rocks. And then you can see these beautiful layers. These layers are 1 millimeter thick. And then when we looked at these rocks in detail, they're really fine grained. They're not even sandstone, they're not sand grains, they are grains of 60 microns or less, and then they're muds basically. And these rocks are mudstones. And to get mudstones to form layers like this, usually on Earth, usually requires them to be forming in water. So you have sediment delivered from rivers depositing in standing body of water. So this is our evidence that there were lakes. And at this stage, we only had about 15 meters of rock like this. Now we've driven through almost 200 meters of rock that look exactly like this, really finely layered rocks. And they tell us that the lakes that existed in Gale Crater probably lasted hundreds of thousands, if not several million years. So we have absolutely the conditions to search for life. What else? So here we have, this is a simplistic view, but we imagined that there was a lake filling Gale crater early in its history, and we had rainfall or snow on the crater rims that supplied sediment to rivers and sediment and water to the rivers, and this fed into the lake and built out deltas into these lakes. Then what we're interested in doing is we want to understand the chemistry of the rocks, and we want to find out whether there's any organic chemicals in those rocks, you know, precursors to life, basically. So this shows you, so Curiosity basically has a Black & Decker drill on it. Well, much more complicated than a Black & Decker drill, but here's the drill bit. This is actually an image taken on Mars. We regularly take images of the drill bit on Mars, and this is only a few, it's under a centimeter across, I think 7 millimeters or something, and I forget exactly, but this is actually a picture taken on Mars to look at the wear on the drill bit. And here is Curiosity actually positioning itself to drill from the, so the drill is on the end of the arm, and it's positioning itself to actually drill into these rocks. And here you can see the drill hole. This was the first ever drill hole on another surface outside Earth. It's amazing. You can see, and it drills about 6-7 centimeters of the Martian surface, and you can see the reddish color is just on the Martian surface. The rocks themselves, the rock powder, is actually green. We've now drilled many, many times, and you can see all of our many wonderful drill holes. And the one thing you will notice if you look at this carefully is that the colors change of the drill tailings. So that's the rock powder left behind after drilling. You know, the central core is put into the chemistry instruments on the rover, but these are the drill tailings surrounding. And you can see different colors, and those colors are representing different chemistry of the rocks, basically. Most of these drill holes are in those lake mudstones, and whilst the physical character of the lake mudstones looks exactly the same, they're finely layered mudstones, the chemistry changes. And what that means is either the chemistry of the lake water has changed through time, you know, different elements coming in, maybe climate change, or that later, after the lakes vanished and the rocks were laid down and the rocks got turned into, the sediments got turned into stone, later there was flow of fluids through the rocks, and that changed the chemistry. And we don't know for sure. There's simple things that we would do on Earth that we can't do on Mars. So that's still a mystery, and we have different hypotheses. But what's amazing is to be able to characterize this different chemistry and mineralogy through these drill holes. And in addition, we've been looking for organics, and in several of the drill holes, for example, Cumberland over there, Mojave, and some more recent ones, Curiosity, using its instrument called SAM, has discovered simple organic compounds likely delivered, and that organic compounds don't mean life, they're just carbon containing compounds, probably we think delivered from meteorites, but the fact that you can discover organics in extremely old rocks on Mars with a robot is just extraordinary. And you know, these rocks are 3.5 billion years old, so that's just extraordinary. So where are we now? Oh, sorry, my computer keeps doing this, so apologies. Where are we now? We are in a place called Glen Torridon, and some of you will be familiar with the word Glen Torridon. It's actually a place in Scotland. At the moment, we named map areas that we've been using for mapping the landing site of Curiosity by places around the world that were famous geologically. And when we got to this area, which was Curiosity's main exploration site, it didn't actually have a name. And so they said, the leaders on the mission said, oh, we need a name. And I suggested Torridon, after a very famous geological site in Scotland, which has very, very old rocks, not as old as on Mars, but about 1 billion years old, and they have lakes, etc. And so the name was picked Torridon. And as a result of that, what happens is that when we analyze a rock, when we look at a rock, it's named after a place in that associated with that site, basically. So at the moment, all our rock names are places in Scotland. So for me, it's very bizarre. If I go to Scotland, I'm driving around, I see all these road signs, of little villages and things. And for me, they're actually rocks on Mars. And so this is what we're exploring at the moment. And this is the beautiful terrain, very austere. It's not wet. It's very, very different to Glen, Torridon in Scotland, which is very wet and very green. And we're very excited to look at these rocks because they contain clays, and clays are very good at containing organics. And so we're exploring that at the moment. And this is a curiosity. This is a picture taken by the HiRISE camera. And you can see that the HiRISE camera on the Mars Reconnaissance Orbiter was able to actually take images of the Curiosity rover, and through successive images actually showed it changing position. You can actually see the rover tracks in this image. It's just amazing to see that. Remember, the rover is about 3 meters by 1 meter in size. And here we are. This is in Glen Torridon. We climbed onto this little hill, and we had this amazing drive where we climbed up an angle of 31 degrees to get onto this plateau. And then we had this extraordinary view. So we're standing on these beautiful rocks looking across this spectacular scenery. Just to give you a sense of scale, an amateur has basically taken these images and inserted an astronaut. This is the astronaut Mark Watney. And you can see the scale there. So that's to give you some sense of scale. This is landscape, and you can see Mark Watney is standing. I wouldn't stand there, that's not very safe. And you can see multiple Matt Damons or Mark Watneys in the distance, just giving you a sense of scale. So you get a sense. Mars in our images always seems to be much bigger than it actually is. And what's happening next? So we are currently sort of in this location over here. In the next few years, we'll be driving here, looking at these rocks here, which are very interesting, containing sulfate minerals. We'll be clambering up this hill, and hopefully in the next 3 or 4 years, we'll be exploring these rocks up here. And we have no idea what these rocks are. We have many hypotheses, but it's not until we get really close to them and can image them in detail with our cameras and analyze them that we will understand what they are. All of this, all the rocks over here, suggest that Mars was very warm and wet. Our hypothesis is that these rocks over here indicate Mars drying out. And so this transition from here to here records a major climate change on Mars from wet to dry. And then we think that these rocks over here, this little finger of rocks coming out here, is another wet episode. So it's just another transition back into a wet episode. And obviously this is really interesting for habitability and searching for life. And here's just showing some beautiful pictures of this landscape that you can see over here, imaged recently, and that we'll be exploring in the next few years. Oh, lots of wind action. Here's a beautiful dust devil image recently, wandering around that landscape, image with our navcam cameras. And what's next? Well, next is
the Perseverance rover.
And here you
heading
can
to
see the
Mars,
launch of
ready to
Perseverance.
ride a column of fire and smoke on its way to the red planet.
And liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the red planet.
The Perseverance.
And so what's Perseverance doing? It's doing something very different to Curiosity. So Curiosity has discovered habitable environments. And as I said, Mars 3.5 billion years ago, 3.6 billion years ago, was likely warm and wet. So we're going to go to a site that's thought to be about 3.7 billion years old and explore another crater lake called Jezero. What we're interested in is looking again for evidence for life. And the key difference between Perseverance and Curiosity is that Perseverance is actually going to collect rock samples, leave them on the surface of Mars, and a future mission or a future set of missions are going to recover those samples and bring them back to Earth. The thing is that we don't think it's going to be very easy for a rover to discover life on Mars. We don't think that we're going to get macroscopic life. We're not going to find, we're always looking for dinosaur bones and we're never going to find a dinosaur bone. What we're looking for is microbial life, some minuscule evidence for life or chemical signatures of life. And for that you need samples and you need to analyze them in Earth laboratories. So we want the sort of life that formed very, very early in Earth's history, around 3.5 to 4 billion years ago. So we're not going to find fish, we're not going to find leaves, but we might find microbial biosignatures. So on modern day Earth, we find microbes built what we call these things like stromatolites. So these are modern stromatolites in Shark Bay in Australia. And these are when microbes growing on the seabed basically trap sediment and grow these columnar features. And we can actually identify them in rocks on Earth going back 3.5 billion years ago. So this is a famous site in Australia, Pilbara. And these dome-shaped things, this is a cross-section through one of these stromatolites. Amazing to think this is the modern day. This is 3.5 billion years ago. And these are layers of sediment that were trapped to form these domes by sticky microbes. And we hope maybe we might be lucky that Perseverance might snap an image with its lovely cameras on the surface of Mars, but more likely we'll get maybe chemical signatures brought back in the samples that come back to Earth that we can analyze in Earth laboratories. So this is just a picture, very similar landing system to Curiosity, but the one key difference is that Perseverance has a special radar, where as it's landing, without any human influence, it's taking pictures off the surface and it can position itself. So it knows exactly where it is by taking pictures and comparing them to pictures previously. It does automatic reconstruction with the radar, and then it can actually veer and it can go away from hazards. And this means we can land in a much smaller area and can get to the sites of interest without huge drives. So this is the rover. It's very much looks like Curiosity, but has a whole new set of instruments. It doesn't have the complex instruments that Curiosity has that does do the in-lab analysis, because it's going to be bringing the samples back. But it does have an amazing arm with a whole new system. Sorry, this keeps happening. So let's just whole new set of instruments to measure the chemistry, fantastic cameras, and a whole new coring system because it's got to core these specially. So here's the camera, the Mastcam Z camera. I'm on the science team of this. This is a geology camera taking those amazing landscapes that we'll be seeing in a few years' time after February. And this is the turret that you can see here, which has the coring system on it. And we're just going to show you a quick video, just showing you the drilling and caching animation. Soon I'll be done. So here we're ready to deploy. Here's the mast, and now the arm is going to maneuver itself. So remember, all of these actions have to have computer code. They can't be directly commanded. We want to drill in this beautiful rock over here, so it's going to position itself on the rock. We now drill into the surface. Collect a core, and this is now brought back to the rover, and it's now put in a whole new sample handling facility. So we dock, and it's transferred to a whole new system that transfers those samples into special tubes. So we now go into the sample handling facility, the cache system, and these are now positioned into different tubes, which will then be subsequently left on the surface of Mars for future return. And now we put it into storage. There's the storage. So we're going to have something like 43 tubes, and we aim to bring back 30 samples from the surface of Mars, perhaps by the 2030, 2031. Now the rover's driving with those tubes, and it's going to take them to a depot site where a mission in 2026, 2027 can recover them and put them into Mars orbit. Okay, so this is the turret. You can see the stabilizers and the drilling bit in the center over there. Very complex system for drilling. And this is where the sample tube is handled and stored, basically. So those copper-colored tubes are the storage for the tubes, because remember, those tubes are going to be left on the Martian surface and have to withstand all sorts of damage, etc., and the harsh Martian environment, so that it can be returned within the next 10 years. So they're built to last 10 years, basically. And this is that whole sample, the cache handling facility, the storage assembly, the handling arm, the dispenser volume, all of these different things. Very, very complex system to make sure, you know, these are the most expensive samples that will have ever been collected. It's not like chucking a rock that I collect on the beach into my rucksack that I normally do. So what about the landing site? Well, here's a quick video about the landing site, and it's called Jezero Crater. I'm going to let the project scientists talk to this.
This flyover was produced from NASA images taken from orbit. The blue circle indicates the area the rover will likely land. The arcing hills in the center, about 1,600 feet high, and are the rim of Jezero Crater. The goal of Mars 2020 is to learn whether life ever existed on Mars. It's too cold and dry for life to exist on the Martian surface today. But after Jezero Crater formed billions of years ago, water filled it to form a deep lake, about the same size as Lake Tahoe. Eventually, as Mars climate changed, Lake Jezero dried up and surface water disappeared from the planet. An ancient lake is a fantastic place to pursue our goal of looking for possible Martian life. On Earth, lakes are filled with living creatures. Evidence of that life is often preserved in the mud and sand deposited on the bottom of the lake. So, we use the rover's instruments to explore the rocks of the ancient lake bed. Here we can see evidence of the former lake. The canyon cutting through the crater rim was carved by a river. As the water entered the lake, it slowed and dropped the sand and mud it was carrying to form the fan-shaped delta. The white line is a path the rover might follow in its first 2 years, called the prime mission. During this period, we'll use the rover's science instruments to analyze the lake sediments. After we explore the delta, we hope to investigate the shoreline of the former lake. To get there, we have to traverse around a sea of modern sand dunes. From this perspective, you can see former shorelines curving around a headland. We can picture waves in Lake Jezero beating on a sandy beach. And finally, we will press on to the crater rim. Jezero Crater formed when a large object collided with Mars, excavating rocks from deep in the Martian crust, exposing them in the rim for us to study. These rocks would have been hot shortly after the impact and may have hosted hot springs. Deposits from these springs would be another target in our search for possible ancient life on Mars.
So river deltas are exciting because they're habitable environments on Earth. In fact, 70% of the world's population actually live on top of deltas. So obviously, we're not looking for humanoid life forms, but certainly they're excellent places to look for microbial life. And in next year, we'll be exploring Jezero Crater and the delta within it, which is, you know, truly exciting. And then what's next? Firstly, we have the ExoMars Rosalind Franklin rover mission in 2022. The UK, Britain is playing a huge part in that, and at the top of the mast you can see the cameras of the rover. Those are our UK instrument, the PanCam camera built by scientists at UCL and many other universities throughout Britain, and the UK leads on that, but it's also been built by all the instruments are put together by European nations and also with Russia. So it's a joint cooperation with Europe and Russia. And here you can see the PanCam on the rover being assembled onto the rover, due to launch in 2022. And then what next? Eventually, I'm certain that humans will go to Mars. Maybe not till the 2040s. Who knows how far you can go as a geologist, but one person I think who may have a chance is Jess Watkins. Jess Watkins, I worked with her, she's a friend of mine on the Curiosity rover team. She's actually a geologist, I worked closely with her, and she got chosen a few years ago to join the astronaut corps, and she's now learning to fly fighter planes and learn to be a proper astronaut, and she's very, very busy, very exciting, and who knows, she may be the next person to go to the moon and maybe onto Mars. We'll have to see, but that's exciting. It's such an exciting time to be a planetary scientist. Thanks very much. That's all from me.
Amazing. Thank you so much, Sanjeev. The questions are literally flying in. Seb and I were desperately trying to write some down as quickly as they came in. We have got so many questions and only a little bit amount of time. So Sanjeev, brace yourself.
Okay.
You ready for the questions from your audience? And just a big shout out actually to everybody. Thank you so much for putting your questions up and also for telling us where you're from. We've had London, brilliant. We've had all sorts of, we've had Bavaria, we've had Ireland, we've had the far north of England, we've had Saffron Walden. So you're all very welcome. It's amazing to have so many people here. We realised that this webinar reached its capacity quite quickly, but for everybody who has registered, you will get a recording of this. So you won't see this live now, but you will hear me saying this in your recording. So we apologise that you couldn't get on and that you weren't able to ask questions, but you'll get the recording this afterwards. Sanjeev, you're just too popular. What can I say? Okay, right, Seb, first question, please.
Question from Ewan and Rowan from the far north. Will people ever set foot onto Mars in our lifetime and find microbial life?
I think we'll go to Mars because it's really the only place that we can actually go to in the solar system easily. Well, it's not easy, but readily. Whether we'll find life, I don't know. It's a question I often get asked. We just don't know. You can't put a guess on that. But you know, we've only looked at a few places on Mars. We haven't really had the tools to look for life absolutely. So we're just going to have to search. So if we don't find life with perseverance, it doesn't mean it wasn't there. It just means that we haven't looked hard enough.
Perseverance is key. Amazing. Right, next question, Seb.
A question from Raphael. Why do you become a geologist and which is your favourite part?
Good question.
Why did I become a geologist? Well,
Yeah.
two reasons. I really like the outdoors. I like being outdoors. I like going hiking and climbing and stuff like that. And geology was something you could do with that. But also, when I was studying at A-levels, I couldn't really decide which science I was interested in. I kind of liked them all. I like physics and I like chemistry and I like biology. And what's nice about earth science and planetary science is it brings all of them together. So you work with all of them. So actually, these days, I work with physicists and chemists and biologists and mathematicians. And it's wonderful to be able to combine all those different sciences.
Amazing, that's good. Actually, there was a question as well. I need to remember. We were writing. We've gone analog. We were just writing down on bits of paper. But somebody asked a question. I'll find out who it was. Oh, here we go. From Manav. He said, "What sort of scientists and engineers work in your team?" So that's a really good point from what you've just said.
Well, we have everything. Remember, the rover is built by mechanical engineers, etc., instrument engineers. We have computer scientists and computer engineers. We have process engineers, you know, how to work at how to do things, the logistics. And the science team, we have geologists like myself, but we have chemists who analyze the chemistry of the rocks. We have physicists who look at physics. You know, for example, Perseverance has a ground penetrating radar. So we have physicists who are interested in the radar. We have instrument physicists. So the wonderful thing about it is it brings scientists and engineers from all walks of life and different fields together with a common aim, basically, is to make a successful mission. And it's wonderful. I love working. So I do a lot of operations. I'm what's called a long-term planner. I do strategic planning, and I work very closely with the engineers, and I love working with them. And they always think that geology is very hard. I actually think that what they do is much harder, but I don't tell them that.
That sounds very sensible. And I have to say, actually, Sanjeev, you have given me the best ever excuse for being late in replying to an email, because you said I was busy doing stuff with Mars, and that beats the whole "it got lost in my inbox" excuse. So you win the prize for the best excuse so far. Okay, next question, Seb.
Question from Daniel. What is the biggest rock you have found?
What's the biggest rock you've found? Oh my goodness me. I don't really know. We've seen so many rocks, whether, you know, there's whole outcrops and whole mountain signs. Sometimes we found loose rocks. I think interesting rocks is that sometimes we found these really shiny metallic rocks, and they're actually iron meteorites. So that we find them on Earth too, but we found these really beautiful shiny rocks. And those are meteorites that have come from out space and hit Mars and formed impact. That's really exciting.
Can you work out where they've come from, or do you just know they've come from elsewhere?
Yeah, so we don't analyze those because obviously we get iron-rich meteorites on Earth, and so there's no point in analyzing the rocks from space meteorites that you can analyze on Earth. So we don't analyze them in general. We're just interested in the Martian rocks.
Fair enough. Okay, next question.
Question from Ahmed. Why do we send rovers to Mars?
Sorry, I missed that.
Why do we send rovers to Mars?
And not to other planets.
And not other planets. So I think we send rovers to Mars because Mars seems to be the most Earth-like. So if we're looking for life, ancient life, what do we look for? What does life look like? So what we're using our understanding of life on Earth to look for similar things on Mars. And because we have rocks on Mars the same age as we find ancient life on Earth, microbial life on Earth, it seems like a good place to look. We might be completely wrong, and we might, so there's other places in the solar system. So, for example, some of the moons of Saturn and Jupiter are thought to have a subsurface ocean, an ice shell, and so people would like to go there to look for life in those oceanic water. But Mars seems to be a good place to go, and it's easier to reach than those moons of Saturn and Jupiter.
It's a good enough excuse for me, I reckon. Right, Seb, next question.
Question from Lauren from London. How long does it take for a spaceship to get there?
Okay, so it takes a spaceship we try to go when the planets are aligned in a good way, that it's relatively close. And so it usually takes about 9 months. So actually Perseverance launched 9 months or less. Perseverance launched in July 30th, and it's going to land on February the 18th. It's all very precisely worked out. We really understand the mechanics of that really well. The engineers do, I don't, I'm a geologist, but the physicists and the engineers really understand that well, thank goodness. Don't get me anywhere near that, and we will land precisely on February the 18th.
That's amazing.
Question from Revent. Would water instantly turn to ice on Mars?
No, it would actually evaporate immediately. So if you put it there, it would just evaporate into the atmosphere.
Okay, I'm going to read out this question because it's quite a technical one, but it's a very good one. So this is from Daniel, and it said, from the perspective of a geologist, what do you think about the tectonic and volcanic history of Mars? Will Olympus Mons erupt again, and will the Valles Marineris grow larger?
Ooh, that's a very good question. And you know what?
Earth Sciences at Imperial.
I don't necessarily know the answer to that. So I think it's debated as to whether there's active volcanism on Mars at the present day, and I haven't kept up with the field. So that's outside my field. And as a scientist, one should always be ready to hold up your hand and say, I don't know the answer, because you can't retain everything in your brain. I don't know, but so people are searching for very young volcanics, and I think there was a paper recently that was suggesting there was maybe some volcanic activity on Mars in the last million years, but we don't know at the moment. I don't know it's certain. In terms of tectonics, we do have faults on Mars, and there's a current mission on Mars called InSight, was a geophysics mission, which actually has an instrument from Imperial on it, a seismometer, and that's looking for Mars quakes. So like earthquakes, Mars quakes, and that's perhaps caused by motion of faults and tectonics, etc. So whether Valles Marineris will get deeper, I don't know. Maybe nobody knows, but that's what we do exploration for.
That is the point of science, isn't it?
Yeah.
Unanswered questions. Sometimes we never know. Right, this is a good one.
Another question from Ishan. What happens to a rover when it finishes its job?
So sadly, well, we carry on. So it never finishes its job. We carry on as long as the rover lasts, basically.
Oh.
And eventually rovers run out of power. The battery goes. So, for example, the Mir rovers, Opportunity, for example, lasted a huge amount of time. So it hadn't been expected to last that long because Opportunity and Spirit, they were powered by, they had solar panels, and the idea was that the solar panels would get covered in dust, and so they would get less efficient. But what happened was that you had these dust clearing events on Mars due to wind action, and so the solar panels lasted much longer. So opportunity lasted a very long time, much longer than lasted. With Curiosity, it's different because we have a plutonium battery. It's powered by radioactivity, and that will progressively decay through time. So, you know, I expect Curiosity will last another 5 years or so, and it'll get progressively less efficient, basically. And then what happens is that new trendy rovers come along, and everybody wants to work on a new trendy rover, and all the money goes to the new trendy rover, and everybody forgets the old rover. Kind of like being a parent, really.
I was going to say, it's like the story of my life.
Yeah, exactly. Tell me about it.
Amazing. Okay, we've got time for a few more questions. Are you happy to carry on, Sanjeev?
Oh yeah, no problem, no problem.
Brilliant. Okay, right, go on, Seb. Which one are you going to go for?
Question from Susan. Could a human land on Mars?
Oh yeah, I think they could easily land a human on Mars. It's a bit dangerous. So I think, you know, space agencies like NASA don't want to risk it until they absolutely know. I mean, it's risky landing our rovers, so you can imagine what it's like with humans. So, you know, there's been a lot of analyses and tests going on, and we don't know about hazards on Mars too. So, for example, and you know, we have to have the conditions. We have to be able to make oxygen for astronauts to breathe, and actually make rocket fuel for them to come back. You know, space agencies, I'm going to send astronauts on a one-way trip to Mars. But yeah, it's absolutely doable.
Fantastic. Right, this is a good one. Okay, from Hassan, what is the most unusual thing you've found on Mars?
Oh, that's a really good question. What's the most unusual thing? You know what? Funnily enough, I don't like finding unusual things because we can't explain it. And then your physics and chemistry let you down. There is one rock from early in the mission, Point Lake, that we never understood. No matter how many images we took of it, and we looked at it for a little bit, we didn't have the tools to understand it, basically, and so we basically had to leave it with a big question. What I really like is, you know, we've seen features that look like features I see in Earth rocks, and that means that I can use my understanding of geology and physics. Physics works on Earth and on Mars, it's the same, and so we can explain it in physical terms, and that's what I really like.
Yeah, that's good. That's that one. There we go.
A question from Carrie. How does Curiosity know what to take photos of?
Okay, so Curiosity does not know what to take photos of. We command Curiosity to take photos. So what happens is that after it's driven, let's say it's on a drive day, at the end of the drive, Curiosity uses its navigation cameras to automatically take a picture of the whole landscape, what we call a 360-degree panorama. The next day, we get that black and white image, and we use that to help us pick targets, areas that we want to get close range imagery of, or high resolution imagery. We can't take full color images of the whole landscape because it's too expensive in terms of, you know, what happens is that the data is returned to Earth via links with satellites, and we're limited as to how much link we have, basically. There's a data limit. So, and also, you know, the memory, can you imagine your mobile phone, etc. You have a memory, amount of memory. So obviously Curiosity's memory gets filled up very quickly with all these pictures we're taking. So we actually have to select areas in the navigation camera image that we use to make higher resolution images with. So we select that, the science team selects that.
I see. Right. Another question.
Another question from Emily. Is there any evidence of life anywhere else in the solar system, like a moon?
Of Saturn or Jupiter?
No, so no evidence so far. What we're really interested in is, and there's some missions going now, planned to go to, I was hearing about a mission to Europa, the Europa Clipper, and hopefully launching, I think in 2024, but I may have that completely wrong. I'm terrible with numbers. And that will go to the moon of Jupiter, Europa, and Europa is thought to have a subsurface ocean, and it will explore the physics of that moon, and apparently there seem to be these plumes coming out of Europa that might be emissions from the subsurface ocean, and the idea is that it could the mission could actually fly through one of these plumes and measure the chemistry. Pretty exciting, pretty crazy, but you know, at the moment we don't know.
Okay, we've got time for a few more questions.
Question from Ethan. If you're looking for microbes on Mars, why would you not look at ice caps?
So that's a really good question. So the issue with this is that when we go to Mars, we don't want to take life from Earth to Mars. That would be a false detection, basically. We don't want to discover life on Mars that's from Earth. And the problem with landing in the polar regions is that when your spacecraft lands, it's obviously going to melt the water or in the ice caps. And so you could readily transfer. You can't, you know, we make our rovers and landers very, very clean. We can't make them completely clean. And so there's something called planetary protection, that you have to protect Mars from Earth microbes. Because otherwise, you know, if we plant microbes from Earth onto Mars, we'd never discover whether there was life on Mars, basically. So at the moment, we're not allowed to go to anywhere where you have ice or polar ice caps or running water or brines or something like that. We have to go to these desert areas and look for past life.
That's really interesting. I did not know that. Right, a couple more.
A question from Raphael. Do you think we might discover new chemical elements on Mars?
I don't think we can do that with our rovers. We don't have the instrumentation for that. I think we'd have to bring samples back. That's a question for a chemist, basically. But yeah,
Nicely deflected. But actually, that leads into a question from Charlotte. Why can't you bring samples back from Mars yet?
Oh, that's so difficult. So imagine we're just about at the stage of being able to explore Mars. Obviously, you know, we have to have immense containment facilities. You know, if you bring those rocks back, they have to be contained, they have to be safe, they have to not transmit anything from Mars to Earth again. So we don't know what's in those Mars rocks. We don't want to put alien microbes all around Earth. It's just a very difficult problem. So basically, we land a rover on Mars, but then you have to launch something from Mars back into Mars orbit. We haven't done that yet. Okay, so what will happen with this joint European NASA mission is that Perseverance will collect the samples in 2026. A mission will go to 2026-28. A mission will go to Mars, to Jezero, land, and out of it will come what's called a fetch rover. That's being built in Britain by Airbus. This will go and collect those samples, take them back to that lander, and put them into a Mars Ascent Vehicle, a MAV, that will launch those samples into orbit. And then we'll have a third mission in 2030, 2031, around then, that will collect those samples from Mars orbit. Each of those components is very, very expensive. And so what you don't want is, if there's a failure at one point, you don't want to spend lots of money with all the other components. So they build it in 3 different stages so that you can contain it. Because, for example, if Perseverance fails and isn't able to collect its samples, which you hope obviously doesn't happen, there would be no point in sending the other missions, basically.
Okay, we're just about out of time, so we've got one more question, which is quite a deep and meaningful question.
Final question from Ishin. What is at the core of Mars?
What's at the core?
Oh, we don't know. We don't know. That's to be worked out yet. So I'm sure the geophysicists, and there's geophysicists at Imperial who work on these issues, have some ideas. That's something I haven't retained in my brain, so apologies.
But why not? You know everything else.
Oh yeah, you know, you aging brain. You at the moment I'm busy with rover operations, so I barely think about the core of Mars. I think 6 centimeters below Mars. That's it. So I'm sure it does have a core, and it must have had a core early in its history, because we thought that Mars had a magnetic field early in its history, etc. So and that core probably cooled and solidified, And so, yes, but we need geophysics missions, and InSight might give us insight into that problem. But yeah, we need to learn lots more about that.
Fair enough. Thank you very much. Well, we are just about out of time. Thank you so much, Sanjeev. That was literally out of this world. I loved all those photos. It just looks like a seascape and a landscape. It's amazing. It's bizarre to think that that's, you know, that is literally another planet. Thank you to our amazing audience for all your questions as well. And I would like to thank the team behind the scenes, Fliss, Tori, Lorna and Amanda on the whistles and bells, making this all work for me and Seb here at the coalface. Sanjeev, let's just finish on a thought. As a geologist, what would you say to any people out there who are thinking about studying geology? What piece of advice would you give them?
Yeah, just find out what interests you. You know, earth science, you know, geology is a bit narrow, so we really call it earth sciences now. Earth and planetary sciences is very wide. Explore what's interesting you. So there's, you know, you can do geochemistry, geophysics. We have a whole degree program in earth and planetary sciences at Imperial. You might be interested in biology, so you can study fossils, you can search for life on Mars. They all bring in these very, very different skills. And the key is that you're able to talk to different groups of scientists. And we all bring our skills together to address these fundamental questions and be curious, you know, be really, really curious.
Literally be curious, like the rover. Thank you so much, Sanjeev. So good night from Sanjeev. And it's good night from me, and good night from Seb. Thank you very much, everybody, and I hopefully see you soon, either in person or online at another Imperial event soon. Thank you very much.
Bye.